Having looked at ways of measuring the total curvature and come to our conclusion that we have a flat universe, we now actually want to go and look at tests of the scale factor. And one thing I'm just going to note before I start here is that I'm doing this in a particular order, which is that I'm talking about how you measure the curvature, and then I'm talking about how you measure the scale factor. Now, in practice, of course, these are two scientific fields which have gone hand in hand, and so people have been measuring scale factor evolution and they've been trying to measure curvature via different techniques at the same time. So this doesn't actually mean that this is the historical order that these things happened, but I think it's pedagogically more valuable to actually do one than the other. In practice, these things have happened together. And so if I just look at my flat universe, imagine we do have dark energy in the form of lambda. That should give me an exponential change in the scale factor. If I have matter, I have t to the 2/3. If I have radiation, I have t to the half. Note, of course, if I also have dark energy which is not lambda, I have something else here. You know, you can solve the Friedmann equation for any particular equation of state parameter you like, and it's not necessarily even simple, right? You can have W, which is your equation of state parameter. You can also potentially have W dot, right? It doesn't have to stay the same with cosmic time. So, you know, to crude expectations, if W equals -1, then I have here the exponential. If W equals minus 0.8, I have something else. And so what I need to go and measure, therefore, is I need to go and measure the scale factor. And primarily, we're interested in the scale factor and its derivatives. So A dot, and A double dot. So in other words, scale factor, velocity, and acceleration. And of course, the scale factor comes straight from the redshift. So the redshift gives me the scale factor. That's my observable. I'm then interested in its derivative, which comes from the Hubble constant, or the Hubble parameter more generally. And that's A dot over A equals H, or A dot over A at T equals now is equal to H naught. So that's the velocity, it's the rate of change of the scale factor. And then I'm interested in the acceleration or the deceleration of the universe. And this leads me to something called the deceleration parameter. And this is a little bit more complicated to understand, this one. And so the idea of measuring a deceleration parameter was that before we had much knowledge of what the universe was doing, we wanted something that was kind of physics-free. So this is, in a sense, a physics-free measure, although you can put physics back into it, and we will do that in a minute. But it also has a sign convention which is historical but important to note. And so the principle is, what if I expand the scale factor around the current point? So I take A of t, and I write that that is approximately equal to A of t0 plus dA by dt at t equals t0, t minus t0 plus a half d2a by dt squared, again at t equals t0, t minus t0 squared, plus etc., go on forever. And then I divide this by A of t0, and therefore I get A of t equals 1 plus h naught t minus t naught plus 1/2 of q naught h naught squared t minus t naught squared. And so this is where I come in. My scale factor is then that function of those, the scale factor itself, its derivative and its second derivative. But in doing that, I have to introduce this parameter q naught. And q naught is equal to minus a double dot a over a dot squared. Which is equal to minus a double dot over a h squared, remembering that h is a dot over a. And this is therefore, this expansion here is the physics-free bit of the measurement. So I can measure h naught and q naught independent of physics. But there is also a link to the makeup of the universe. And that is the following. If I take the acceleration equation, I have the following. And if I just divide that by h squared and multiply by minus 1, minus 1, and note this is just a sign convention. It reflects the fact that a positive deceleration parameter indicates a slowing down universe, because at the time people came up with the deceleration parameter, they expected the universe to be slowing down, hence the minus signs here and here. So what I therefore get here is I get minus a double dot over a h squared. So that's my deceleration parameter, is equal to minus 4 pi g over 3c squared e plus 3p. Okay, and now I'm going to give away the answer to one of last week's problems as well, because what I can do here, I can write this also out as being 1/2 times 8 pi g over 3c squared e plus 3p. I can note that 8 pi g over 3c squared, 3c squared, h squared, the h squared here, h squared. This is just equal to 1 over the critical density. If you go all the way back up here to the beginning of the lecture, it's just 1 over that. So I can then do the following. I can now sum over the components of the universe. In other words, I can do minus a double dot over a h squared is equal to q naught is equal to a half times the sum over w here of 1 over the critical density times E plus 3p. But I know my equation of state P equals WE. So I can also write that as Q naught equals a half times the sum over W of omega, W 1 plus 3W. And then I can sum over W equals 1/3 naught minus 1 for R, M and lambda to get that Q naught is just equal to omega R0 plus 1/2 omega M0 minus omega lambda 0. And so my Q naught is in fact directly related to the densities that I've just mentioned earlier in the lecture. I can now tell you what Q naught is by summing in that this is 0.27 and this is 0.73, and I can work out what my Q naught is, and indeed it tells me that I should have an accelerating universe. Also note, I said I'd give away the answer to one of last week's problems, that Q naught equals 0 when omega M equals 2 omega lambda. So the transition from acceleration to deceleration doesn't happen from acceleration to deceleration doesn't happen when omega M equals omega lambda. Because of the different equation of state parameters, they don't cancel each other out. You have this twice factor. So omega M is a half of omega lambda, or omega lambda is 2 omega lambda. Get it the right around. This is right. So, that tells us some quite important things, but it also tells us that if we can measure acceleration, or we can make a prediction for acceleration on the basis of the densities that we've seen. So in that sense, there are parameterizations up here that are physics-free parameterizations of the scale factor, A, its derivative, which gives you H naught, and its second derivative, which gives you Q naught.